Game theory and its real-life applications. Game theory can be applied to many real-life situations. In this video, I will be analysing the incentives of athletes to use performance-enhancing drugs in the Olympic Games. Doping was prevalent in the 2004 Athens Olympic Games, and it has been branded one of the dirtiest games ever. So why exactly did these highly skilled athletes feel the need to cheat? To allow us to analyse this, first we need to make some assumptions. Let's assume we have two athletes of equal ability which are competing against each other in the Olympics. The athletes have two strategic choices, to dope or not to dope. We assume the player that takes the drugs wins the race with certainty. Thus, if both athletes take the drug, they are once again equal in ability, levelling the playing field. We assume both athletes decide simultaneously before the competition whether to dope or not to dope. Finally, we assume perfect information and rationality. A key aspect of a game is the payoff a player can potentially receive depending on their choice and their opponent's choice of strategy. Their payoffs are in monetary form. There are three outcomes for each athlete which can be represented by payoff functions. Firstly, the amount they receive for winning, which is equal to 200, the amount they receive for losing, which is equal to 0, and the amount they receive for being exposed as a drug user, which is equal to minus 100. We also must consider the probability of being caught for using drugs. We will denote this as P and make it equal to 50%. We can represent this knowledge in a matrix. If both athletes choose to dope, then because they are of equal ability, they would both win and so split the prize money. But they would also have to consider the probability of being caught and the monetary cost associated with this. Therefore, the payoff if they both choose to dope would be 1/2 W minus PC. If one athlete dopes and the other doesn't, the one that uses drugs will win, so their payoff would be the full amount of prize money, again minus the probability of being caught and the cost of being exposed as a drug user. The athlete that doesn't dope will have a payoff of 0, seeing as they will lose. If neither chooses to dope, then they would both win and therefore would receive half the prize money each. So if we add the monetary values chosen for this particular game, the payoff matrix would look like this. If athlete 1 chooses to dope, athlete 2 can dope with a payoff of 50 or not dope, but would receive 0, so would choose to dope. If athlete 1 chooses not to dope, athlete 2 will choose to dope, because 150 is larger than the payoff of 100 if they were to choose not to dope. If athlete 2 chooses to dope, so will athlete 1, as 50 is larger than the payoff of 0 if they were to choose not to dope. If athlete 2 chooses not to dope, athlete 1 will still choose to dope, because the payoff of 150 is larger than the payoff of not doping of 100. Dope-dope is a Nash equilibrium, as neither athlete can gain by a unilateral change of strategy. Individually, both athletes are worse off than if they were to both not dope. This is an example of the tragedy of the commons. Because the payoff for doping is greater than the payoff for not doping, despite what the other athlete chooses, each athlete has a strictly dominated action of doping. This type of game is referred to as the prisoner's dilemma game. The optimal outcome for both athletes and for society would be if neither used performance-enhancing drugs. To achieve this, we would need to change the payoffs so that there wasn't an incentive to dope if another athlete was to dope. Using theory derived from the Becker-Freeman model, doping could be eradicated from sports by increasing the probability of being caught, which we refer to as P, and also the severity of punishment, denoted by C. This could be achieved by doing more extensive checks covering a wider range of athletes and increasing the length of the ban from sports or by imprisonment.